Okay, let's start talking some more about graphing rational functions. Okay, what's a rational function? We talked about that in class before. A rational function is a ratio of polynomials. Okay, now let's assume that I've taken my polynomial function, my rational function, and you remember whenever we have two polynomials and we're dividing one by another, we can get what? A quotient plus a remainder divided by whatever the divisor was, or the denominator if you wish, with what? The degree of the numerator strictly less than the degree of the denominator here. R of x ended up standing for what? It standed for remainder, right? Okay, so I'm going to assume that we have this done here, and as a special case, I'm going to start out assuming that the quotient is going to be ignored here. I'm going to focus on the second part right there. Let's see what's happening to functions of that type where I've got a ratio of polynomials where the degree of the numerator is strictly less than the degree of the denominator. Okay? So in this specialized case here, I'm going to call the degree of the numerator, the remainder part, the r of x, m, and the degree of the denominator, the divisor there, n. So m is strictly less than n. So I imagine writing r of x this way in descending order, r sub m, x to the m, plus r sub m minus 1, x to the m minus 1, all the way down to plus r naught. So these r's here with the subscripts are what? The coefficients of the polynomial. So again, written in descending order. And then I'm going to do the same thing with d of x. It's in descending order also, only its coefficients will be represented by d's because the polynomial there is called d of x. Okay, now I'm going to play a little trick here. What I'm interested in is knowing what happens as x approaches plus or minus infinity to this thing. So let's imagine x is getting really, really large in absolute value, positive or negative, but it's getting large in absolute value. I want to see what's happening to expressions of this kind. Okay, here I'm going to play the trick here. I'm going to divide in both the numerator and denominator by x to the n power. Now, x to the n power ought to be the highest power of x that appears in any of these terms. Okay, remember that the degree of d of x is larger than the degree of r of x, and this is going to be the highest power term here. Notice also that these leading coefficients, here that I'm circled here, neither of those are equal to 0, otherwise we wouldn't have written them at all. If they were zeros, they wouldn't even be there. Okay, anyway, so I'm going to divide by x to the n power. Since that's just a single monomial term, I can take that x to the n power and divide it into every single term in both the numerator and denominator. And when I do it right here, x to the n divided by x to the n is 1. So I've got d sub n times 1, which is d sub n. X to the n minus 1 divided by x to the n is x to the minus 1. So I've got d sub n minus 1 x to the minus 1 power. Remember, when you're dividing, you're subtracting exponents, okay? So on each of these terms, imagine subtracting n from the power. So I would get what? Into x to the 0, x to the minus 1, x to the minus 2, x to the 1 minus n, x to the 0 minus n, which is really minus n. Now I'm doing the same thing up in the numerator, so I would get r naught, x to the minus n, r sub 1, x to the 1 minus n, and so forth, all the way to the leading term up here in the numerator, r of x, and that would be x to the m minus n. Now I'm going to circle all these where I have a negative exponent on x. Do you notice the exponent on x is negative in all these except for what? Except for that guy right there. That has actually x to the 0 power. All these have a negative power on x. Now, just like in our last video, if I've got a negative power on x and x is approaching plus or minus infinity, these would go to what? 0. So this would go to what? This means approaches, by the way. Okay, in this context, that means approaches. Okay, that approaches 0, that approaches 0, that approaches 0, 0, 0, 0. All these approach 0. So what does this whole thing boil down to? It boils down to 0 divided by d to the n. Remember, d sub n is not d to the n, but d sub n. D sub n is not 0. 0 divided by a non-zero number is 0. So the point is that this thing, in the case where what? The degree of the numerator is strictly less than the degree of the denominator, what happens is, as x approaches plus or minus infinity, expressions of this type approach 0. So what we say is y equals 0 is a horizontal asymptote for the graph of y equals r of x over d of x, okay? So this is going to be a horizontal asymptote. So just like in the last video, in the extremes to the left and right, the graph of something like this is going to be approaching the x-axis. Okay, now a couple of quick definitions here before we go on. So some further simplifying assumptions I'm going to make here. A polynomial that cannot be factored in the real numbers is called irreducible. Okay, and we would only speak of this if we were talking about a real polynomial anyway. So I say in the second part, if a real polynomial is irreducible, then it must be quadratic, that is, have degree 2 with imaginary zeros. Okay? So the only real polynomials that are irreducible are quadratic ones with imaginary zeros. Okay, this is a fact that we can derive from the fundamental theorem of algebra together with the conjugate zeros theorem, but I'm not going to go through the details on that. Okay, let's take a couple examples here. X squared plus 2x plus 2 is irreducible. If you actually use the quadratic formula to find the zeros of this polynomial, you can see this is a real quadratic polynomial. Its zeros are what? -1 plus or minus I. Okay? This thing does indeed factor. We know every polynomial factors in terms of its zeros, so it would factor this way. But how come this isn't contradicting what I said just above? Well, these are not real factors. This is actually irreducible. Okay? This is the only way to factor it, by the way, in the complex numbers, which also includes the reals, right? Okay? How about this, though? X squared minus x minus 1. This is not irreducible. That's also known as reducible. This actually factors, right? Well, once again, you could set that to 0, and you could find its zeros using the quadratic formula. You'd find the zeros are 1 plus or minus the square root of 5 over 2. And so, because this is a monic quadratic, we would actually have x minus 1 plus the square root of 5 over 2 times x minus 1 minus the square root of 5 over 2. So these are the zeros. This is actually reducible because these are real factors. These are both real numbers. I was not introduced here, right? Okay? Now keep that in mind then, so understand what reducible and irreducible means here. Let's take a quick example here. Can the polynomial p of x, which is 2x cubed minus 5x plus 11, be irreducible? The answer is no. Okay, it's what? It's a real polynomial. What's its degree? Its degree is 3. Its degree is 3. 3 is greater than 2. This isn't quadratic. Okay? Once again, the only irreducible polynomials, real polynomials, are what? Quadratic polynomials with imaginary zeros. And I should mention here, I guess I made that sort of wrong, also linear polynomials are irreducible. Okay? All right? In a trivial way. Okay? But this is degree 3. No way. It's not going to work here. Can this be irreducible? Okay, so in other words, what I'm saying up here, this can be factored some more. That can be factored in the real some more. Okay, in fact, this is going to have a real 0 because you see it's going from the, what, lower left to the upper right. Okay, it's going to have to cross the x-axis somewhere. Okay, now this doesn't cross the x-axis somewhere, but it's still irreducible. Why is it irreducible? Why is it irreducible? Why is it not irreducible? Because its degree is 4, which is greater than 2. Okay, let me give you a factorization of this, by the way. You could maybe try to find one yourself, but I'll give you a real factorization right here. You can try it and see if it doesn't work there. And that actually works. By the way, these are both irreducible themselves, okay? But the big thing, this thing, is not irreducible, but these are, okay? Okay, so I say it here. An irreducible real polynomial must be quadratic or linear, okay? So I actually messed up. I should have said here, a real quadratic, well, anyways, you get it now. Okay, an irreducible real polynomial must be quadratic or linear, okay? And neither of these are quadratic or linear, so they must be reducible. That means you can factor them some more in the reals, okay? By the way, a quick way to think about this from this little factoid over here, okay? Ax squared plus bx plus c, we're assuming a is not 0, so it actually is quadratic, is irreducible if and only if, what, b squared minus 4ac is actually less than 0. That would come directly from the quadratic formula. That's the value we call the discriminant that's underneath the square root sign. Okay? Alrighty, let's go on here. Here's some assumptions that I'm going to make for my graphs here. My numerator and denominator are going to be products of linear polynomials. Okay, so the only irreducible factors that I'm going to be using for a while will be linear ones, so quadratic ones will not be involved for now. I'll show you what happens later with those. Here's another assumption I'm going to make here. R of x over d of x is reduced. Let me give you an example of what would happen if you had r of x over d of x that was not reduced. Suppose r of x is x squared times x minus 1, while d of x is x squared times x minus 2 cubed. I would have you notice here that this function does not exist at 0. If I tried to let x equal 0 in here, I would have what? 0 for this factor, 0 for this factor. I'd be dividing 0 by itself, and there's no such thing. However, probably the most natural thing in the world that would occur to you is to cancel the x squareds out here. When you do cancel those x squareds out there, you're making an assumption. The assumption is that x is not equal to 0. You can't cancel zeros, but you can cancel non-zeros. If you did cancel those out here, then you would get a related function, which is what? Reduced, okay? Reduced here, but I would notice that there's actually a difference between these functions, because once I divide out the x squareds here, this related function, this reduced function, actually exists at 0. Unlike this, where it does not exist at 0, this actually does exist at 0. If I let x equal 0 here, I actually get negative 1 over negative 8, which reduces to 1 over 8. This function exists at 0. This does not. So there's difference between the two, isn't there? Okay? If I was to actually graph this thing, if I was interested in graphing that, okay, I would actually graph this simplified thing, and then I would punch in a hole in the graph at this at 0, 1/8, because this function does not exist at 0. That's all you would have to do is punch in a little hole like that. So with that trivial change between these two, I'm going to be making my assumption throughout that r of x over d of x is already reduced, so we don't have to consider this situation where you have to punch a hole in the graph. Okay? It's easy enough to do, so I'm not going to bother with it. We'll just assume we don't run into that situation. You can deal with that if you want it. Okay? Under these assumptions, the domain of r of x over d of x is the set of all real x, I should say real of x here. We're going to be interested in graphing these, so we're only interested in real numbers. The set of all x such that d of x is not equal to 0, okay? And the idea here is that you actually take d of x and set it to 0, right? And kick those out of the real numbers. That's how you get the domain here. Now, this holds even under this situation without these assumptions here. This is going to be the domain of my function. But under these assumptions, I'm also going to be talking about vertical asymptotes here. Okay, let's have a quick one here. Suppose r of x over d of x is x over x plus 3 times x minus 2. Okay, what would be the domain? It would be all real numbers except what? Negative 3 and 2, right? All real numbers except negative 3 and 2. Let's use interval notation. Minus infinity up to minus 3, union what? Minus 3 to 2, and then what? Union 2 to infinity. So I'd be punching holes in the real number line at what? Negative 3 and 2. Okay? Now, we can think about, we're going to be thinking about in a future example here, I'm actually going to graph this in a bit, what's going to happen as x approaches negative 3 or 2. Okay? Now, in general, the vertical asymptotes of r of x over d of x are the vertical lines x equals a constant, I'm calling that z sub I, I equals 1 to n. There may be multiple ones here, where the z sub I are the real zeros of your denominator, okay? So in this problem above here, so z stands for zeros here, okay? In the problem above, we have what? What are the zeros of the denominator? They are the numbers -3 and 2. So I could say maybe z sub 1 is -3 and z sub 2 equals 2. That's the notation I'm using here. Okay, now what are the vertical asymptotes? The vertical asymptotes would be the vertical lines x equals -3 and x equals 2, right? So those would actually be vertical lines, x equals -3 in our graph and x equals 2. So just like the type of thing that happened in our previous video. Okay, now we're going to be talking about this, okay, just a minute. Graphing r of x over d of x, which I'm going to call h of x. I'm going to assume under this situation, just re-emphasizing here, that the degree of r of x is strictly less than the degree of d of x. Here's what we're going to do to get our graphs. It's not going to be that bad. Find the real zeros of the numerator. That's the r of x. These are going to be the zeros of h of x. I've also assumed that this is reduced, like I've mentioned here. Find the vertical asymptotes by finding the zeros of d of x, okay? Again, this is reduced, okay? Okay, find the zeros, so doing like we were doing just a second ago. Then what we're going to do to get the idea of the graph of this, it's not going to be perfect or anything, sample the function h of x at values of x between the vertical asymptotes, and we're going to do that at points, the values of x other than at the zeros of r of x, because we already know the value of the function at those places. It's 0, right? Okay? And then I'm going to show you here how we can actually get a graph of h of x here, r of x over dx, by using this information above and the fact that, remember, we have a horizontal asymptote for this thing, which is y equals 0. Remember the very first page? Okay, we'll be doing that in the next video.